Hello and welcome. Today we're going to talk about how to solve systems of equations using substitution. A system of equations is when you have multiple equations lined up and you need to find a solution to them usually. A solution to a system of equations looks like a coordinate point. So for example, a solution to a system might look like this, 3, 5, where 3 is an x value and 5 is a y value. This is a solution if and only if it both works for the first equation and the second equation. So if I were to plug in 3 for the first equation and then 5 for the y for the first equation, I should get a valid equality. It doesn't happen in this case, this is just an example, but in general, that is how you know a solution is actually a solution to a system. So let's see what that looks like. Over here, we have the equation y equals 2x plus 1. Now we also have the equation x plus y equals 7. So we're going to try and find a valid x and y value that makes the top one true and the bottom one true at the same time. One method of doing so is to use substitution. In substitution, what we're going to do is focus on getting a variable isolated on its own. For example, y here is all on its own, which is good. Once we have one on its own, we can actually look to the other equation and start to replace. So because y is equal to 2x plus 1, when I see this y down here, I can think of that as a 2x plus 1. So what I'm going to do is write the second equation, all the same, x plus, but instead of y, I'm going to put this 2x plus 1, because y is equal to 2x plus 1. They're the same thing. I'm just switching it out. And I like to put parentheses. It won't matter in this case, but it does matter a lot when you have negatives and coefficients and so on. So I have x plus 2x plus 1 from the first equation. And now I don't forget to continue writing. I wrote the x, I wrote my replacement for y, now I need to write my equal sign and my 7. Then I can just focus on simplifying. If you notice, I now have only a single variable, x plus 2x plus 1 equals 7. I don't have any y's anymore. I replaced it out. And so I combine my single variable, 3x plus 1 equals 7, and I solve for that variable. I'm going to get rid of the 1 by doing the opposite, minusing 1, 3x equals 6. I'm going to get rid of the 3 by doing the opposite of multiplication, division. And I get x is equal to 2. Now, this is not a final full solution. This is the first component of our solution. We need both an x and a y value. We have two equations, so we have two parts of our solution. What am I going to do to find this next part of my answer? Well, I'm going to take this x equals 2. I'm going to plug it into one of the original equations. It actually doesn't matter which. I'm going to choose the first one because y is isolated, so hopefully that makes it convenient and easy. So I'm going to look over here at this y equals 2x plus 1. I'm going to write it exactly as it is, y equals 2, except instead of an x, I'm going to substitute. I'm going to replace the x with a number 2, because I know that's what x is equal to, and then a plus 1. Then I can simplify. This is equal to 4 plus 1, which is equal to 5. And therefore, I have a full and final solution of parentheses 2 for my x value, comma, 5 for my y value. If I were to plug in, I could double check and make sure that works. I won't do this for all of the examples, but you always can. What that looks like is this. I have a 5 for my y value, so I put a 5 right here. And I check, is that equal to 2 times 2 plus 1? Because I replaced the x with the 2. Yeah, 5 is equal to 4 plus 1. And then we'll check the second equation. If I do, instead of x, a 2, plus, instead of y, a 5, does that equal to 7? Yes, it does. And so because it works for both the top equation and the bottom equation at the same time, this is a full and final answer to our question. Let's try some more. So here we have the system 2x plus y equaling 10 and x minus y equaling 1. We can still solve via substitution. However, it's not going to be quite as easy. In the previous example, we had a variable on its own already. We don't have that here, so we cannot simply switch out. So I'm going to try and isolate a variable. I think the easiest variable to get on its own is going to be this x. It's already an x, there's no numbers next to it, and there's only one little thing next to it, this minus y. And to get rid of that minus y, to get x alone, I'm going to do a plus y to both sides. What that gives me is that x is equal to 1 plus y, or y plus 1, same thing. Now that I have isolated a variable, I'm basically where I was at with the last problem at the start. I'm going to take this x And I'm going to replace in the other equation. I will not go into the same equation. You'll just keep looping around forever. So if you find yourself plugging in and just getting numbers or not really getting anywhere, you probably plugged into the wrong equation. You have to switch to the other equation to obtain new information. So I'm going to replace the x value in this first equation with this x value, which is actually a 1 plus y. That's going to look like this. I write the 2 just as it was, 2. And then I put a parentheses, and this is why I was emphasizing parentheses before. Instead of x, I put 1 plus y as my quantity. And I don't stop there. I have to write everything else from the first equation still. I still have a plus sign. I still have a y. I still have equal to 10. And if you notice, now I have a single equation with one variable, just the y, no x hanging around. So I can solve this like normal. I'm going to distribute this to 2 plus 2y plus y is equal to 10. I'm going to collect my y terms. 2 plus 3y is equal to 10. I'm going to isolate y by getting rid of all the numbers next to it. Minus 2, minus 2. 3y is equal to 8. And then I'll divide by 3 on both sides. Y is equal to a fraction, 8 over 3. And that's okay. That's how it is. And I'll write it just like that. You could write this as a decimal if you like, but I find fractions to be easier to work with and a little more clear. So I'm going to leave it as is. Now, that is not my final answer. My answer for any system of equations is going to have as many components as there are equations. I have 2 equations. I better have 2 parts to my answer. And in fact, I need to find an x value for this. Now, where I plug this y value in doesn't matter. Unlike earlier where I had to plug into a new equation, once I get this number, I can plug it in anywhere I want. And I think the most convenient place to plug this number in is going to be right here, because x is on its own, and it's what I want to find out. So this will say that x is equal to 1 plus, and then instead of y, I get to write the number 8 over 3. Now again, you can let your calculator do the work if your teacher's fine with decimals, but I like fractions, so I'm going to do a little fraction simplification. I'm going to get a common denominator of 3, so I'm going to times 3 over 3 on the 1. That says 3 over 3 plus 8 over 3. I'm then able to now combine these terms because they have a common denominator. I'm going to get that x is equal to 11 over 3. I add across the board on the top, and the denominator does not get affected. And so my full and final answer is both of these combine into a coordinate point. I would say my answer is 11 over 3 for an x value, and then 8 over 3 for my y value. And with that, I'm finished with this problem. Let's try some more. For this problem, we have y equals 0.5x minus 2. And we also have x plus y equaling 6. Now this is nice because y is all on its own, so I can probably easily substitute. It is kind of annoying though, because I do have a 0.5 here. A lot of students don't like decimals. For now, we're just going to ignore that decimal and let it tag along, and we'll see what happens. So to begin, I'm going to take this y value, which is in fact equal to 0.5x minus 2. I'm going to replace the other y value with this. Y is equal to this, so I can replace it with that. And so I'm going to write my second equation as x plus, and this is the only difference I'm going to make. I'm going to put a parentheses 0.5x minus 2. And then write everything else exactly the same, still equal to 6. Don't forget to write everything else. Now here the parentheses didn't do much, but as we saw before, sometimes it matters. So I make it a habit to write them. Here I'm going to have x plus 0.5x minus 2 is equal to 6. Now, if you're comfortable with decimals, you can just add up here. You get a 1.5x plus 2 divided by 1.5. But let's say you aren't comfortable with decimals. You don't like working with them. Maybe you're not allowed to use a calculator or something like that. There's a nice little trick to get rid of decimals. I'm going to take everything in this equation and multiply it by 10. And I'm allowed to do that because it's going to happen to both sides. Why do I do that? Well, you're going to see. For the x, when I multiply by 10, I get a 10x. For the 0.5x, when I multiply by 10, this decimal, deci standing for 10, just moves 1 to the right. And so I actually get a plus 5x minus not 2, because we still have to distribute the 10 to everything, minus a 20 is equal to a 60. Now, this is still the same equation, just rewritten to look a little nicer and not have any decimals. And I can combine like terms to get 15x minus 20 equals 60. I will add 20 to both sides to get rid of that minus 20. 15x is equal to 80. And then I'm going to divide by 15 on both sides to get rid of that 15. And this leaves me with x equaling 80 over 15. And I can simplify that, in fact. And so I'm going to get rid of a 5 on the top and a 5 on the bottom. And when I do that, I'm left with a 16 on top and a 3 on the bottom. So my answer for my x value is going to be 16 over 3. And it's a fraction, but that's okay. Again, if you would rather work with decimals, just throw it in your calculator, get some decimals, and move along. Now, I'm not done because I have not gotten my second part of my answer. There's two equations. I need two components to my answer. So I'm going to take this 16 over 3 and I'm going to plug it into one of the equations we started with. And I'm thinking which one will probably be easier? I would say probably the second one. Not the first one, even though y is alone for the first one. I don't like that this decimal is here. I don't want to do 0.5 times 16 over 3. That doesn't sound particularly fun. So I'll stick with the second equation, which has no decimals. And so I'm going to write 16 over 3 instead of x plus y is equal to 6. Now I have to get y alone, so I'm going to minus 16 over 3 on both sides. That leaves me with y equaling 6 minus 16 over 3. Again, if you like decimals, throw it in the calculator. I'm going to convert it to a fraction for the 6, make it a 3 over 3. That's going to give me 18 over 3 minus 16 over 3, which means my y value is equal to 2 over 3. And so my full and final answer is going to be the coordinate point, 16 over 3 for the x and 2 over 3 for the y. And then I'm done with this problem. Let's try some more. Let's check this one out. So over here, the y is isolated on its own, which is pretty nice. We have y equals negative 3x plus 4, and we have 2x minus y equaling negative 2. The only annoying thing I see happening here is that there's a lot of negatives floating around, so we're just going to be very careful. That's all. And so I'm going to, like usual, going to take this isolated y and use what it is equal to replace the y in the other equation. And that's going to give me the following. 2x, because I'm just rewriting what I had before, minus, just like before. And then this is where having parentheses is so helpful. I'm going to throw parentheses right here, and I'm going to put negative 3x plus 4. All of that y value gets jammed in there. Now I am not done. I have not finished writing this equation. I still have to write the equal sign and the negative 2. Don't forget to do that part. Otherwise, you'll be sitting there staring at an expression with no equal sign, no way to solve, nothing to do. So we continue. I have a 2x, and how does this negative interact with these? All I do is distribute to each item. So a negative 3x makes a positive 3x, and a negative 4, and then I have equals to negative 2. I'm going to combine all my terms. I have 2x plus 3x to give me 5x minus 4 equals negative 2. I'm going to get rid of that negative 4 by adding 4 to both sides. This leaves me with 5x equaling a positive 2. Negative 2 plus 4 is a positive 2. And then I divide by 5 on both sides. X is now equal to 2 over 5. I like fractions. I'm going to leave it as is. You can write it as a decimal. It would be 0.4, but I'm going to leave it as a fraction. Now, once we have our x component, we're just going to throw it back into one of the original equations and get our y component. I think the first equation looks nice here. Y is all alone. There's nothing crazy happening on the right side, so I'm going to go with that. I'll write the y, I'll write the equals, I'll write the negative 3, and then I'll write my ever so helpful parentheses. And instead of x, I'm going to write the quantity 2 over 5. And then I don't forget to write the rest of my equation, plus 4. And then I simplify. This is going to be a negative 6 over 5 plus 4. I cannot combine these. Again, decimals calculator, whatever works for you. I'm going to get a common denominator, 5 over 5. This is going to say negative 6 over 5 plus 20 over 5. Common denominator, I can now combine. Negative 6 plus 20 gives me a positive 14 over 5 for my y value. And with that, I can now write my full and final answer to this question as the coordinate point 2 over 5 for the x, comma, 14 over 5 for my y. And I'm done. Let's try some more. So in this situation, we have y equals 2x minus 3 and y equals negative x plus 6. This is kind of interesting because we have y alone for both equations. Usually you will see these earlier on. I chose not to do these earlier on because these are deceptively easy. There's a nice and easy trick where you just set one equal to the other. But that goes around the idea of what's happening. So I'm going to put it in the same context as I did the others. I have a y alone. I'm going to take this quantity of 2x minus 3, which is equal to y, and replace or substitute my other y out down here. So all I'm going to do is write the second equation exactly the same, but replacing y with 2x minus 3. That looks like the following. 2x minus 3 from that y equaling negative x plus 6. And again, it's a nice easy shortcut. You just set them to each other and all that, but that doesn't help you in general when systems are less convenient and require more work. But let's continue. With this, we can solve further by combining all x's. So I'm going to add an x to both sides to bring them all together. That gives me 3x minus 3 equaling 6. I now isolate the x. 3x is equal to 9 if I add 3 to both sides. I divide by 3 and I get x is equal to 3. And then like always, I'm going to take that 3 and I'm going to plug it in to one of the original equations. It doesn't matter which one. I don't like having negatives in my variables, so I'm going to go with the first one. Let's see what happens. So I have y equals 2, and then I replace my 3, parentheses 3, in place of my x, minus 3. That's going to give me 6 minus 3, which is a nice 3. And so I have a nice whole number answer of 3 for x and 3 for y. And again, this is a pretty easy solution because these are both equal to y. It's really convenient, easy to access, but it's the same idea underlining all of this. I'm replacing the variable I've isolated into another equation and solving. Now, there are a couple outlier situations which give you strange answers, either no solutions or infinite solutions, and we're going to see what those look like. So for this problem, we have y equals 2x plus 1, and we have 2y equals 4x plus 2. Now, if you're astute, you might notice something happening here. There's a relationship between these two equations. The second equation is actually just double of the first equation, and that's going to matter. But if you don't notice that and you can't jump ahead and answer it right away, that's okay. We're just going to do our normal system. We're going to figure out how to solve this equation using substitution. I see y is isolated, and so I can take this quantity on the right and use it to replace the y in the other equation. That's going to give me the following. 2 parentheses, now I do my replacement, I do my substitution, 2x plus 1 instead of y. And then I write the rest exactly as was, equals 4x plus 2. Now I distribute and simplify. 4x plus 2 is equal to 4x plus 2. That's strange. Well, I'd normally want to move all the x's to the same side, so I'll do a minus 4x, and lo and behold, I have that 2 is equal to 2. Now, do not be confused. This does not mean that 2 is your x value, or that the coordinates 2, 2 are your answer. That is not the case. What is the case is that you found, in your process of trying to solve for an x or a y value, a true statement. This is always true. You found that 2 is equal to 2, and that is true regardless of what x and y are. And so I will write in this situation that I have infinite solutions. There are infinitely many possible combinations of solutions for x and y. X and y could be anything at all, and this will work out. And that's because these are the same equation. These will always coincide. They will always be overlapping each other, and so it will always be an infinite solutions. Whenever you have the same equation twice, which will give you, if you go through the work and find an equation that is always true, then you have an infinite solution. Let's try one more. Here we have y equaling 3x plus 1 and y equaling 3x plus 4. In this situation, I have y equals on both sides, so you could do a little shortcut of setting them equal to each other. But if you are observant and you look, these look pretty similar, and they're actually both linear equations. So if you wanted to look ahead and guess what would happen, you could probably guess that these two equations, having the same slope and a different intercept, might look something like this. And those would be parallel lines, which never intersect. A little foreshadowing for what's to come. So let's just solve. Let's say we're not sure. We don't have a guess for what the answer is. We're just going to, use brute force. I'm going to take this isolated y value, which is equal to 3x plus 1. I'm going to replace the y value in the other equation. Again, you could just set them equal to each other. That's fine shortcut. This is going to give me 3x plus 1 equaling 3x plus 4. I want to bring all the x's to the same side, like always. And when I do so, minus 3x, the x's go away, similar to the last problem. But something's different. I get that 1 is equal to 4. And that is never true. 1 is never equal to 4. These are different numbers, so I cannot say they're the same. And so what's my answer? My answer is certainly not 1 comma 4. That's not what's going on here. I do not have an x value of 1 or an x value of 4 or either of those for a y value. What's happening is when trying to find an xy value, I get a contradiction. I get an incorrect statement that is never true. And so my answer for this question is no solutions. These are two parallel lines that will never cross. These will never give a valid answer. And with that, we're done with the problem. All right, as a recap, in order to solve a system of equations, which is just multiple equations in a row, using substitution, what we do is we isolate a variable. We get a variable alone. X equals y equals, doesn't matter. We're then going to take whatever x or y is equal to and replace the corresponding x or y value in our second equation. So go into our other equation and start switching numbers and variables out. When we do that, we're going to have to solve that equation, but now we can actually solve it because there's only one variable. Once you do this substitution, a variable goes away and you're left with only one. Then I'm going to solve and find a number. And when I get that number, I'm going to plug back in once again. So it's a second layer of substitution, but this time it's just a number. You can plug that number into one of your original equations and solve for your second number. And that will give you a coordinate pair of an x and y value that gives you a full and final solution. So I hope that these systems of equations are a little less intimidating now. They can only throw so many curveballs and tricks at you. And if you go with this system, it's always the same. It's always the same. It may be the case where you have to deal with some fractions, there's some ugly decimals, you get an infinite solution or something, but it's always the same system. So at least you have some consistency.